All right, so the next topic is bandpass data converters. So all of the data converters we've talked about up to this point have been low pass types, which means they digitize a signal from DC to some bandwidth B. And now what we're going to do is we're going to take a look at digitizing like a narrow band or over a bandwidth that, maybe at an RF frequency. And so just real briefly, I wanted to review some IQ signals which we covered earlier in the semester. Um, Specifically, if you write a IQ signal like this, you can get AI of t times cosine of 2 pi fc. What's the fc stand for? Yeah, it's the carrier. So if you look, this is amplitude modulation, and when you put the two signals together, it's called quadrature amplitude modulation. Again, we went over that. What's the point of doing transmitting signals like this? Yeah, you get more information, and of course you can't transmit the 180-degree phase shift because then things cancel. All right, so um, that's all the review at this point. So what you can do then is you can take this signal and you can run it through a multiplier, and then you can have a local oscillator here, LO, that's at some sinusoidal frequency. Let's just say it's at cosine 2 pi fc times t. Then I'm going to use some trigonometric identities to down convert. Notice we went through this when we talked about the vector rotating around the complex plane. You got your in phase, you got your quadrature, they sum together and get something in the middle. What's the phase shift between the in phase and the quadrature? What's the phase shift between the in phase and the IQ signal? It's only 45 if they're both the same amplitude, right? And then if the amplitudes vary, the phase angle varies, and then the amplitude of the IQ varies, right? Everybody remembers? Okay, so I'm going to just take this real briefly and then show you. And where's someplace, what was it we talked about with QAM? What, does everybody remember the constellation diagram and the jitter and signal to noise ratio, and then how to transmit things like in your modem, your wireless at home, those kind of things. So I'm going to use a couple trigonometric identities there. Let me just go ahead and rewrite this real quick as, right, times cosine because we're demodulating, which is AI of t times cosine of 2 pi fc times t times cosine 2 pi fc times t plus AQI of t. So I'm going to ask you a question, so get ready here. Cosine of 2 pi fc times t, sine of 2 pi fc times t. The first fc trivial question. What is the well, let's ask a little bit more challenging question. I was going to ask you, where's the carrier? There's the carrier for the local oscillator demodulation. Okay, so does anybody notice in the book and here I drew it as being in phase with the input signals? The I and Q are definitely 90 degrees out of phase, but I wrote this down, this cosine, as being in phase as well. Does everybody see that? Okay, does it matter if it's in, does it have to be in phase? No, it doesn't, and I'll show you why in a moment. So what I'm going to use is the following identities. I'm going to use cosine of A times cosine of B is equal to 1/2 times cosine of B minus A, and that's plus cosine of A plus B. So keep that in mind when we think about the phase shift of the cosine being different than these two. These two, do they have the same phase shift? they're obviously 90 degrees out of phase, but if I were to add 30-degree phase shift to one, I would definitely have to add it to the other, right? Because that's the whole point of IQ. They got to be 90 degrees out of phase. All right, and then the sine of B times the cosine of A, where that's our LO, is equal to 1/2 times sine of B minus A plus sine of A minus B. If I look at these two terms now, what I end up getting, if I look at the, let's just say the cosine term first, is I end up getting a, let's write it out, AI times of t times cosine of 2 pi fc times t times cosine of fc 2 pi fc times t. And if I add those two together, what do I get? Cosine 0, which is 1. Okay, so now comment on if there was a phase shift in the local oscillator. Would it be cosine of 0? No, but it would be a constant, right? Okay, so I'll just leave 1 in here for now, and then plus, and then cosine of 2 times pi times 2fc times t. And what I'm going to do is I'm going to pass this through a low-pass filter, and I'm going to remove this portion because it's at twice the frequency. Does everybody follow that? Now, if I have cosine and it's not exactly the right phase shift, then that affects my amplitude or scales my amplitude, but it doesn't influence my filtering. All right, are there any questions there? Yeah, so that's why I have the extra 2 there. This one? This one? Sine and cosine? Oh, all right. There we go. Thank you. All right, any questions on that? What's the whole point? Whole point is that I can take this IQ signal, multiply it times the cosine, but wouldn't it be better if I could take this IQ signal and directly digitize it? Or if it was real high frequency, demodulate it to an intermediate frequency and then digitize it? That's what we want to cover in this chapter, okay? Now, let me just, before we go any further, you notice how when we talked about the oversampling ratio, we had, the oversampling ratio in our bandwidth was f sub s over 2 times the bandwidth, we'll call it b. So it's basically the Nyquist frequency divided by the bandwidth b. And that if we shrunk our bandwidth, that we would get a higher oversampling ratio and our signal to noise ratio would go up. Okay, we get the same exact thing here, except for when we look at the frequency range, we're going to be having a frequency that is centered around this carrier, this intermediate frequency, okay? So in order to get good signal to noise ratio, we shrink the bandwidth around the carrier. So we can get really high signal to noise ratio even though it's at high frequencies because we're only going to digitize right around the carrier. So here, if I keep shrinking, my SNR goes up. We all understand that. It gets smaller and smaller. Here I'm going to get the same effect, except my bandwidth is shrinking around the carrier. Okay, one more. Does everybody understand that? Because when I first learned this, I was like, well, this doesn't seem to be very useful because if I'm operating at, this is 2 gigahertz, how am I ever going to get real high signal to noise ratio if my clock's running at 10 gigahertz? That's only like 4 times difference. And that's not the issue. The issue is the bandwidth and the B away from the center, which could be a couple hundred kilohertz. So you could be at 2.4 here and just go out a couple hundred kilohertz and have an oversampling ratio of like 1,000. Okay, so you could get real high signal to noise ratio. Does everybody follow that? Okay, I want to cover one other thing before we get going here, and that is I want to review the sync filter. So you remember our sync looked like this. What was the response for the sync? Right. And so if you plot on the complex plane, you get, here's my unit circle, and then, okay, so help me out here. What is 1 minus z to the minus k also known as? Comb filter. So where do I put the poles and the zeros? Yeah, so I have poles right here, and I have how many? And then where are the zeros? Yeah, they're evenly spaced around here, and I could do the math, and I know some of you have done that during quizzes, but if you have 64, those zeros are going to be spaced by f sub s over 64 around the unit circle. Now you can do, oh, I plugged it in my calculator and I can't find the roots of the 64th polynomial. Well, come on, okay? So then you say, okay, well, what's the point of what is 1 over 1 minus z to the minus 1? Non-delaying integrator. What's the point of that? Cancels out the 0 here, so I get rid of that. Okay, so this we make sense. This gives us a low pass. Oh, this is boring. I know this. Here's what we have, right? And then this would be the number of samples I average. Okay, what I'm going to do for band pass conversion is the following. I'll do this. 1 minus z to the minus k over 1 plus z to the minus 2. I still get my filter. I still got my comb filter that has my zeros there. Except what does the 1 over 1, what is the name for 1 over 1 plus z to the minus 2? It's a resonator. And where are the poles for that? Yeah, plus or minus j. And so what I get from my filter response then looks like this. And this is centered at f sub s over 4 and f sub s, 3f sub s over 4. And there's f sub s over 2 in the middle. And so it's a band pass response. And again, if I have k really big, what does it do? It shrinks these bandwidth. Does everybody follow that? Okay. So before we even go on even further, it's very common to use f sub s over 4 resonators because they're really easy to implement. But tell me some other resonators that I could use here. And what are the, well, I mean, even simpler question. What is the requirement on the location of the pole of the zeros here? Yeah, well, I have to make sure that I can, if I'm using integers, I have to make sure that they're at a point on the unit circle that I can put a pole precisely, because I don't want to put poles on the unit circle unless it's integer math, so that I don't get rounding and that numerical issues, right? So some of the other ones we talked about were f sub s over 6, f sub s over 12, those kind of poles, right? So if I had 12, k of 12, I could put a pole at f sub s over 6, which would be like right here, f sub s over 12, etc., and go around. Does everybody follow? What I'm going to concentrate on is f sub s over 4. Okay, that gets the points across, but if you remember back in chapter 4, when we talked about resonators, we said, okay, here's the band pass. There's f sub s over 4 here. There's f sub s over 6 or f sub s over 3. You could think of other ones then as well. Okay, so let's talk about band pass modulators. Okay, so when we did a low pass, we used an integrator. Okay, here we have a, in our low pass delta sigma, what's the gain of the integrator at DC? Infinite. Okay, so what we want is we want to replace the integrator with a circuit that has an infinite gain at f sub s over 4. Okay, so does that make sense? So let me ask this. If I have this transfer function, 1 over 1 minus z to the minus 1, and I ask you what is the gain at DC, what is it? Infinite. How do I know? Remember, I told you, z over z minus 1, and then you put, 1 plus j omega, whatever, rc, what if it's active, and then 1 plus j omega rc, or if you want to replace that with 1 plus j 2 pi f over fs, you get the same deal. Minus 1, what is this at DC? It's 0, so you get 1 over 0. It goes to infinity. So you need to make sure that when you look at these z-domain things, that they don't look like what the hell is that? I mean, it needs to be like looking at a frequency response where you look at the frequency, oh, I know that's a low pass, that's a high pass, whatever, right? If I look at 1 over 1 plus z to the minus 2, and I say, okay, well, let me get an intuitive feeling for that. I get z squared all over z squared plus 1. And then I'm going to factor this into what? Well, first let's do it like this, right? Yay. And then I say, okay, I'm going to write the first few terms. If I write that, I get 1 plus j times 2 pi f over fs minus j. We'll just look at that term alone. And then that's equal to 1 plus j times 2 pi f over fs minus 1. Then I ask, where's the location of the, where does this go to 0? fs equal, or f equal fs over 2 pi. Fs, it goes to 0 when these two are equal. Fs equal 2 pi. Fs over 2 pi. F equals, yeah, F equals Fs over 2 pi. Right. Okay. No, you can. You can do it directly on the circle. That's what I did here. I'm just trying to give you an approximation. No, I know, but I already did it on the circle right here. I'm just trying to do it a different way. And then you say, okay, well, that's not really Fs over 4. Why? Because for this approximation, the requirement that F much left and F sub S isn't valid. So we'd have to use the higher order terms. All right, so forget that. Okay, so let's go look at the implementation here. And just as I cringe, I'm going to ask this. When I have a parallel LC, when does that impedance become infinite? Yeah, the resonance, what is the resonance? Right? Well, if you're looking at hertz, it's 1 over 2 pi squared LC, right? Now, if I looked at my low-pass modulator, what did I have there alone? Capacitor. What was the impedance of the capacitor at DC? Infinite. So here I'm just putting another infinite impedance, and I'm going to go through and look at the calculate the transfer function. And so I want to I'm gonna do it. Okay, so if I look at the current, I'm gonna call this node here V integrator, just to keep it the same way. I did right there, V integrator, and I get a current coming in here, which is V in minus V integrator all over R, plus minus V out minus V integrator all over R, is equal to, or that's I integrator, that's times V integrator at the resonant frequency. So I'm going to write, okay, so make sure you tell me if you don't understand this. I'm going to write plus V integrator all over this impedance, which is SL times 1 over SC divided by SL plus SC, 1 over SC. Does everybody agree with that? So this is the impedance of the inductor is SL, the impedance of the capacitor is S1 over SC. So it's just parallel impedances, which is equal to SL over 1 plus S squared LC. And this is where you can see that at S equal 1 over the square root of L, this blows up. All right, so S equal 1 over the square root of LC. All right, so does everybody understand where I got this? Does anybody understand? Okay. Okay, what do I do next to get to the transfer function? Because we've done this before. So we got this current plus this current equals the current through the resonator. So what now? I'll give you a hint. Something's equal to V out. Yeah, plus the quantization noise. Does everybody follow that? All right, so then I can go, and ideally, what do I want V int to be? 0. Just like with the integrator, I don't want it wiggling. So I can go then rewrite this as, let's do it slow. We'll write it as V out is equal to V in. And I'm going to do this. You tell me if it makes sense. This line isn't right? Oh, no, it can't be. Yeah. So this plus this, oh, that isn't right, is it? So it'd be this, get rid of this, and then multiplied. How's that? Better? All right. All right, that makes it easier. So let's, just to make sure it's clear, I'll rewrite it. Times SL over 1 plus S squared LC plus VQE. Looking good? All right. And let's see, so what I'm going to do is I'm going to multiply, well, let me cheat and look in the book. Well, I got to factor out the V in, and so we'll do it this way. We'll say V out times 1 plus S squared LC is equal to VQE times 1 plus S squared LC plus V in over R minus V out over R minus 2 V int over R. And then we'll move the V out here. And we get V out times 1 over R plus R plus S squared LCR equals V. What's that? SL. Sorry. Lots of algebra. And then I move that to the other side. So this would be plus SL over R times Vn minus 2SL over R times Vint. How's that? And then last but not least, let's multiply both sides times R over SL plus R. So we get V out times, I'm going to multiply top and bottom of this by 1 over R. So I get VQE times 1 plus S squared LC all over S squared LC plus L over R times S plus 1. Holy crap. And then Vn is plus SLVn all over, I think let's leave that as R, all over S squared LC plus L over R times S plus 1 plus a bunch of stuff times Vint. And I'll point that out in the book. Any questions before I comment? Another day, and I didn't make it through without using algebra. You ever watch when you fly, because I fly a lot, you look in those catalogs in the back of the seat cushion, or back, you know, the onboard shopping thing, and they have all those t-shirts. They're pretty funny to look at, and one of them is another day and I didn't use algebra once. I want to get one that says another day and I couldn't help but use algebra or something like that. All right. So let's look at this. At DC, what is this term here? What is this equation? What is the input? How much of the input goes to the output at DC? 0, right? What's a bandpass converter? That's what we want. However, if S is equal to 1 over the square root of LC, then this term cancels with this term, and then SL over R cancels with the SL over R, and all of Vn goes to the output. Does everybody see that? Assuming we're going to talk about this in a moment, but in next time too, we'll talk about making Vnt constant. This term ideally is distortion, so it's something we don't want. But if you look at what happens to the quantization noise at S equal to 1 over LC, square root LC, goes to 0, right? So S is equal to 1 over the square root LC. This becomes minus 1. 1 minus 1 is 0. So although this denominator goes to L over R times S, the numerator goes to 0. So at the resonant frequency, quantization noise goes to 0, and the signal goes directly to the output. And so the whole point here is that we can make a data converter that digitizes a bandwidth of frequencies, and if we minimize the bandwidth, we can increase the signal to noise ratio. Okay, any questions? And that's shown right here in this plot. And it's showing no noise at the resonant frequency, which is 1 over 2 pi LC. That's the noise transfer function. And I'm going to do a simulation in just a second and show you what the output looks like. But everybody gets used to, what does our normal noise transfer function look like, or modulation noise? Yeah, it looks like this, right? Yeah. Okay, so let's look at a simulation. So let's look at figure 8.4 and 8.5. Properties, 643. Properties, 643. Open Window Explorer, Document, Camtasia. Goodbye. The old digital IC students really like the videos. I keep telling them, you guys don't like them, you never use them, so. Alright. So let's go download that, and that would be right here on the 24th. My guess is the most useful videos are the ones that are project related. Alright. And let's look at 8. Oh, whoops, wrong one. We want this one right here. And let's look at 8. I'm going to look at 8.4 real quick because it's a short little sim. And this is our, I got a question. Why did I put VCM here instead of ground? Yeah, DC, it's a short, right? So I would never be able to get a DC value of VCM there with the DC short through the inductor. Okay. So I'm running at a clock frequency of 100 megahertz, period of 10 nanoseconds. So what did I select the LC to resonate at? 25 megahertz, F sub S over 4. Okay, so we hit run, and then you look at the output and you go, I have no idea if this is right or not. I just see some ones and zeros coming out. So let's look at the spectrum. So I run the same sim, but I'm going to run it for a longer period of time. And you know what? Let's run it even longer. Let's live it up. Oh, it's running 10 microseconds. Never mind. So we get lots of data coming out, and then we go to select this window, view, FFT, V out signal and noise. Notice I have a sine wave at 25 megahertz going in. So let's hit OK. Then let's zoom in by reload plot settings. There it is. Does everybody see that? Let's zoom out a little bit. There's our tone we put in. Let's just verify it's working. Would everybody, well, before I do that, let's see the noise shaping. Boom. So let's go here in noise shaping. Let's go 0 to 50 megahertz. And let's go 5 megahertz steps. Oh, that's right. I'm going to get my tones in here. I didn't discuss that, which are going to be at multiples of the sampling frequency. But does everybody see the tone coming through? Now, what I want to do on the next sim is I want to move this. So this is at 25 megahertz. Oops. If I could get it on there. Does everybody see 25 megahertz? So I'm going to digitize. So wait, what is this tone at, and how do I know? It's at 100 minus. It's all at the images, right? It's at DC plus minus 25, 100 plus minus 25, etc. Okay, so I'll go through, close this. I'm going to modify this and change it to 26 megahertz. Hit run. Select this thing, go up to plot settings, FFT. Where's FFT? Oh, view. Yep. Okay. Then right click, go to, or left click rather. Let's just put it at 50 meg. Yeah, we'll just leave it like that. And then here I go. I'm putting in 26. Does everybody see that at the bottom there? Righto. All right. So what if I put what if I change the DC? Let's say I put the DC at 6.6. What do you think is going to happen? Well, nothing, obviously. Why? Well, wait, we got a resistor here to 0.6. This voltage source physically shorts that node to 0.5 volt, so it's not going to influence anything. But you don't believe me, I can tell. Let's find out. View, FFT, OK, left click, 50 MEG. Let's see, boom. There's my output. If I go here, my output is 1/2 volt. If I can get my cursor on there, it's minus 6 dB. What is minus 6 dB? Half. So even though I put 0.6 in, it's still going to minus 6 dB. Any questions? Yes. Yep. Yeah, so if you have a resistance here, yeah, so this is an infinite Q, right? So if you put a parallel inductor, it kills the Q because you get energy lost in that parallel resistor. You get energy lost in the resistor, right? So you get a wider bandwidth. Yeah, your signal is going to go down. That's, yeah. I don't know if it's right at the resonant frequency, but my thinking is that you would still get an attenuation between this 10K and the shunting resistance. Yeah, if you put a big, but there'd still be a loss because, yeah. And then here as well, the feedback. Let me think, is there anything else we can talk about here? Distortion, but let's move on. So let's use a active integrator, which I'm not going to rederive the transfer function, but let's look at ch8 here. So what have I done? See if the distortion tones go down. I'm using an active integrator to try to keep the integration voltage here constant, and so this will resonate or have an infinite gain at 100 or 25 megahertz. So I expect to see less spikes in the output spectrum. So, but before I go on, does anybody have any questions? So this is an inverting amplifier. At the resonant frequency, what's its gain? What's the gain of an integrator at DC? Infinite. What's the gain of this resonator at F sub S over 4 at the resonant frequency? Infinite. The way to look at this is the energy from the inductor feeds into the capacitor on one half of the cycle, and the other half of the cycle goes back and forth, so you're not putting any energy in here, and so you get a very high Q or infinite gain. Does that make sense? If I take an inverting amplifier and I say, what happens to the gain if I increase RF to infinity? Gain goes to infinity. It's RF over RI. Yay? Any questions? So let's hit roll them. Again, I don't know what the hell that means. So let's go look at the next figure, which is the same exact shim. I put in 25 megahertz here, running for 10 microseconds. Then I'm going to go look at the response. Okay. And let's zoom in a little bit so we get a little bit better noise. So let's go, how about 40 meg? And how about, so let's see, that's 15, 10 meg. And you can kind of see the noise shaping. Let's make this a little bit better here. You can kind of see the noise shaping with the tones coming in. Let's go ahead and save this. Whoops. Let's go ahead and save this and then change our tone. And I'm going to change it to 26. Rerun the sim. Hit select the right trace, view, FFT, OK, plot settings, reload plot settings, and there you see, oops, you see that at 26 megahertz I have my tone, and then you have other tones in here which are related to those limit cycle oscillations. Let me see if I did a sim with the second order. Does everybody agree that's at 26 megahertz? Okay. No. Well, what is that? What I kind of glossed over. I assumed everybody knew what that was doing. What did we put on the output for the low pass? An RC for filtering, right? So we put an RC to filter the signal. Here, what are we doing? We're filtering as well, but with a band pass. Uh, I don't know if it's much worse. Let's see what happens with the second order. Okay, so the second order, which for a it's called a fourth order instead of second order, and the first order is called a second order because you have two poles, right? Because it's band pass, and then for the second order equivalent of the band pass, it's a fourth order because you have four poles, right? So let's see what we get with this one. Great. And then here, run. Yeah, you still have stability issues, but the problem with these is they're more susceptible to phase, clock jitter, and phase noise. So, so let's do FFT, and then plot settings, reload plot settings, and then let's go wider. So I think what we were seeing with the tones was probably due to tones in the output. But here you really see the noise shaping. Would everybody agree? Now notice that if you're going to operate this, your bandwidth's going to be very narrow, so it's going to be digitizing right around the carrier. You're not going to be digitizing out 5 megahertz, all right? That's just not practical in a radio receiver to digitize at 20% of your carrier frequency. Does everybody follow this? Does anybody? Yeah, yeah, but if you're at 2.4 gig, you're not going to have a bandwidth of 200 megahertz, right? You're going to have bandwidths of maybe a few megahertz or something like that, right? Or maybe even 10 megahertz. But having 5% of 2 gig is, what is that? 10% would be 200, so 5, what's that? Yeah, so that's not really reasonable to digitize around. I mean, the reason is because you can't make your antennas and your receivers match over those wide bandwidths with good noise performance. All right, so let me just look at this. Let's wrap up and ask you a few questions. So the simpler one, just to repeat myself, what order is this and why? Fourth order, because 2 poles per resonator. Okay, it's equivalent noise shaping wise to the second order. You get your every doubling, every time you shrink the bandwidth, you get 2.5 bits, even though it's called a fourth order. What was the point of this circuit right here? Yeah, band pass, so I could see the output a little easier. If I go look, I saw what all these ones and zeros were when I did the FFT. If I come over here, I can then plot. Let's plot. So that's what the output looks like. Let's plot the input. And I could zoom in. And you could see that's my hokey way of trying to recover the signal with just a passive filter, just to show that the same signal coming out is what's going in. Okay. Of course, the ringing or the change is the filter's not perfect, right? But I could filter it more, but what's the problem? Yeah, it attenuates. Yeah. Okay. Any questions? Oh yeah, that's a good point. It's 26 meg. Nope, this one's 25. Yeah, but you could easily go, okay, I want to see what's going on here. So you go do this, and you say, all right, well, let's see if we get better filtering using two filters. Got to right click that and call it vout filter 2, of course. Hit run. Double click on that, and then click on that. Boom. Oh, this one's a long sim. Oh, it looks better. A little bit of a phase shift, but filter out more of the noise. You have less of the signal coming through. All this stuff seems kind of magical to me to digitize some bandpass filter. It just seems like wow, you know. So, all right, any questions? All right, we'll see you on Wednesday. Have a good evening.